Here we are. So everyone can hear us. So welcome to old.net. If you're here, drop a comment in to say hello. Do we have our usual regulars? Pop in a comment and we'll wait patiently, not looking awkward here for a second or two to see whether anyone's really listening as the data comes through. So grab yourself a drink or a snack or just listen intently and do nothing, up to you really. Let's see how we go. Give it a minute or two. And I'll check on Twitch that it's coming through as well. Any comments yet? Oh, good, we do. We have people. All right, I think we're good to go. We can now see we have an audience. We have some comments. Thank you, Andrew, for replying. So welcome to Sydney Alt.net, and it is October. Sorry about last month. I was away at conferences and Richard had lots of things on. So yes, sorry we didn't have a session for you then. But we're going to make up for it today because we've got Rahul today to tell us about Open Service Mesh with plenty of Kubernetes goodness as well thrown in on the side. He's just been telling me about how he's been deep diving into Kubernetes, doing monitoring products and that sort of thing. So he really knows how it works. So as usual, we'll have the competition today. So I'm going to listen closely and note down 2 questions as we go. So if you stay to the end, you can get, as usual, 1 of 2 JetBrain licenses if you answer the questions correctly. And as usual, the first person to answer correctly wins each one. So maybe I'll swap across to Rahul now. Are you ready for the screen share?
Yeah, can you see my screen?
All right, I'll just add it in. Let's bring it across. Here we are. Yeah, so if you might look carefully, you'll notice that Richard's not here because his daughter's turning 20 today. So he's doing some stuff with her. So you just have us to keep the show running. But I'm sure we'll manage. So hopefully you enjoy. So I'll put Rahul at the very top here. Let's see, because he's the most important. There we go. And you can see his slides now on the right. So as usual, feel free to ask questions or to heckle or whatever you feel like. Maybe not too much heckling. What do you think, Rahul? Do you like heckling?
Yeah, I do love heckling.
All right, so bring on the heckling. And as usual, I'll put up any comments that that people have and surface them as your voice. So I can stick them up like Andrew's one here. So as we go through, so feel free to chuck stuff in the chat, good stuff, I mean, and I'll surface it for questions as we go. All right, I think we're good to go. Over to you, Rahul.
Sure. Thanks, Jay. All right, I'll start. So first of all, welcome everyone, and thank you for taking the time to attend this session. My name is Rahul. I work as a group product manager at an observability company called Logic Monitor. I specialize in container monitoring and cloud monitoring products. I'm also a Microsoft Azure MVP. So let's look at the agenda, things that I wanted to discuss with you about the concept of service mesh in general, and we'll dig deep into open service mesh, which is one of the service mesh available that you can use. So first of all, we'll cover what the value proposition of a service mesh is, why you should think of incorporating service mesh in your architecture if your workloads are running on Kubernetes. We'll then take a deep dive into open service mesh, and then we'll look at some of the patterns that you can implement using service mesh and open service mesh in particular. Right, so let's start with the introduction. So first, let's start with why you should think about having service mesh at all in your infrastructure. So if you think about a typical application, it's not just the business logic that developers are responsible for writing. So there are many cross-cutting concerns apart from business logic, such as security, communication logic, and monitoring logic that developers need to write as well, in addition to the business logic that they're responsible for. Now, as developers, we are very good at solving business problems, but we are not that good at, we are not experts in things like security, caching, communication, and a bunch of other stuff that needs to go along with the application. So, what Service Mesh does is that it takes away all of those cross-cutting concerns, apart from business logic, that is, and moves all of those responsibilities over to the infrastructure layer. So when you incorporate business service mesh into your architecture, what you would be responsible for writing and maintaining is the business logic, and then other cross-cutting concerns. For example, the encryption of the communication channel between different services, traffic management, uh, rollout strategies such as A/B deployment or canary rollouts. All of such concerns are taken care of by the service mesh. So it makes the lives of developers very easy because they don't have to worry about all of these other concerns. So now that we understand what the purpose of a service mesh is, let's look at the typical architecture of a service mesh looks like. So there are many service mesh apart from open service mesh that is the topic of discussion today available in the market. So some of the popular ones are Istio, Linkerd, that you might have heard of. So most of them follow a similar architecture. That is, they have two components. One is the control plane, and another one is the data plane. So if you compare it to the human anatomy, control plane is like the brain of a service mesh, whereas data plane are like the limbs of the service mesh. So what control plane is responsible for doing is that whatever instructions, whatever configurations you want to send to the service mesh, as an it did, it decides how the service mesh would behave. So essentially, whatever policies you're writing and you're sending it over to service mesh, they're stored here in the brain of the service mesh. That is the control plane. Once control plane gets these instructions from the users on what they want the service mesh to do, it would send instructions over to the data plane. And data plane are sort of like workers that are responsible for implementing those policies. So uh, if you look at it from a deployment perspective, a control plane runs as a service within your cluster, whereas the data plane components, they actually run as sidecars along with your application workflows. So your application packaged in a container is running in a pod. Uh, what the data plane component would be a sidecar that sits along with your application container in the same pod. So that ways it can communicate with your application workload on the same network because it's living within the same pod, right? Uh, Now this control plane would typically have a UI or an API interface through which you can send instructions, and the communication between control plane and data plane, they generally happen over gRPC, using gRPC. And these policies, as I said, would be implemented by data plane, whatever uh, policies you configure the control plane to do. So this picture here is to make things more clearer on how things work within a service mesh. So let's look at a typical request path within a service mesh. So let's say you have three different applications running in your cluster, and these applications need to talk to each other in order to fulfill a request. So when a request comes into the cluster, it would be routed to the pod of the first application. When in a sidecar would intercept the request, communicate to the app container that it is sitting alongside with. And then the app container would essentially uh, try to make a request to another pod. So, for example, here in this case, say a request needs to go from pod 1 to pod 2. So, the app container in pod 1 would make a request to pod 2. What would happen internally is that request, the outbound request, would again be intercepted by the sidecar, and it would be sent to the sidecar of pod 2. The pod 2 sidecar would again send the request over to app container, uh, intercept the outbound request, send it to pod 3, and that's how this whole communication works. So in none of the cases, the app containers would be communicating to other resources, both within the cluster and outside the cluster directly. Every traffic would be intercepted by the sidecar and would be routed via it. And that's how all of the policies, as in all of the benefits that we spoke about of, of the service mesh are implemented. So, for example, the MTLS security between the a pod-to-pod communication. This is how it's implemented because the traffic is intercepted by sidecar. The sidecar would wrap it with an MTLS certificate, send it over to the next sidecar, which would uh, unwrap the certificate, send the traffic over to app container. So this is how things work within the service machine. So now that we know what a service mesh is and how the requests work within it, there are certain limitations on why you might not want to implement service mesh in your architecture. So first of all, it adds a little bit of complexity to the architecture because you have to deploy this another service in your cluster, this service mesh that you need to maintain, right? Apart from your application. Apart from expertise in managing Kubernetes cluster, now you also need to have expertise in managing the service mesh as well. If you look at it, it's yet another application running on your cluster. So you need to manage its life cycle as well. From time to time, you would need to keep upgrading the service mesh. Uh, Likewise, you would need to write more policies than just than just the specs to install your application, right? So now you would be writing more specs than you had to without a service mesh. And as we saw that there is this presence of a sidecar along with your application container, and every request that goes to your application container and every request that comes out of your container is intercepted by this sidecar. So this hop adds a little latency to request, although it's not very significant, but it's something to uh, be cognizant of if you're writing time-sensitive applications. So we spoke about service mesh. So now I'll walk you through open service mesh, which is one of the service mesh implementations. So open service mesh is a CNCF sandbox project. It was initially built by Microsoft, later donated to CNCF. So why you might want to choose open service mesh over the alternatives such as Istio and Linkerd? So some of its key attributes are that it's posed as a lightweight alternative to Istio, that it doesn't add uh, I would say a lot of processing to requests before it reaches the sidecar. So the binary itself is very small, and it doesn't do a lot in terms of processing the request and sending traffic over to the data plane component of it. Very easy to understand and contribute to the. You can go and take a look at its code over at its GitHub repo. It's not a massive piece of code and very simple to understand. Uh, because it is not a not a very complex piece of software. That's why it's very easy to install, maintain, and operate. And also, it's very verbose. So if something goes wrong, you would find sufficient logs and traces emitted by it that you can use in order to troubleshoot it. Another key feature is that you can configure it via a service mesh interface, which is a canonical language or specification format that has been that's built by Microsoft and again donated to CNCF. That a canonical format for configuring any service mesh. I'll talk about it in a little bit more detail now. So let's talk about SMI, the language through which you can configure open service mesh. So uh, let's understand what the backstory of this implementation is. Uh, so what Microsoft did was that it looked at multiple service mesh implementations like Istio, Linkerd, and there are a bunch of others as well. And most of the service meshes actually implement the same cross-cutting concerns. So MTLS connection between applications and canary rollout. Some of the things that I spoke about in one of the earlier previous slides. So most of the service mesh do the same thing, but each of them have their own language or specification format that you need to use in order to configure them. So Istio has its own language or specification format that you need to know in order to configure it. Linkerd has its own. Uh, so in a way, if you write a then if you implement a certain service mesh in your architecture, then you get tied to it. You can't really freely move between different service mesh implementations if you want to. So what Microsoft did was it took all of these common features that all of these service meshes were implementing and built a canonical specification format for it. So, and that's what they call service mesh interface, and is now again another CNCF project. So in a sense, you can write your specifications once, and then you can keep replacing the underlying service mesh implementation if you want to, without having to, write the same policies over and over again in different formats. Uh, and these are just interfaces as in specification formats. There are implementations written for common service mesh, again, like Istio and Linkerd. But then if a new service mesh comes into picture, then you can very easily, as in the community can write implementation, service mesh interface implementation for that service mesh, and then we'll be able to add support for the service meshes as well. Uh, Now, another thing I would like to add here is that service mesh interface, this now the Kubernetes upstream project, one of the Kubernetes special interest groups, took a look at service mesh interface, and they thought that since we know that all of these service mesh do essentially the same thing, and we already have this SMI which abstracts most of these common specifications. Why don't we take them and bring them to the Kubernetes project itself? So bake them as a native object in Kubernetes. So if you take a look at afterwards, you can take a look at the Kubernetes Gateway API, which is one of the new API implement, as in one of the new APIs they are working on. And in the near future, this is what I suspect is going to happen, that service mesh interface is going to uh, be made available as a native API within the gateway API itself. So it might go away as well, and get absorbed into the gateway API. So the way how you configure service mesh, as in how you configure service mesh in the future might change. But for now, as of today, SMI spec exists, and this is the specification that you can use in order to configure open service mesh. So in the architecture, uh, in the sidecar architecture that we spoke about earlier, we saw this presence of a control plane and a data plane. So I would like to take you one level deep inside service mesh and talk about what these control planes and data planes look like. So uh, in many common service mesh implementations like STO and an open service mesh, we find this component called Envoy. Envoy is another CNCF project that was initially built by Lyft and later donated to CNCF. And if you look at its definition on its website, what it says is that it's an open source agent service proxy which is designed for cloud native applications. So nothing. So it's not a component that's been built just for Kubernetes, but it's just a proxy that can intercept traffic and route it over to a destination. So if you boil down this definition of Envoy, what it essentially means is that you can have Envoy act as both L4 proxy and L7 proxy. As you can host it and host it outside of Kubernetes as well, but it has sort of become the de facto data plane of service mesh implementations. So all of these popular service mesh like OSM, Istio, all of them use Envoy as their data plane. And yeah, because it's such a common thing and very easy to configure, it's not going to go away anytime soon. So let's look at the overall architecture of open service mesh, how things work within open service mesh land. So when you install open service mesh on your cluster, you would find that a service called OSM controller gets installed on your cluster as a service. And when you instruct this service to inject a sidecar on your application workload, you would find that it would take the request to create a new application pod and add some more data to add some more specs to the pod creation request. And what that would ultimately lead to is having a pod created that has an Envoy container running alongside it. So if this doesn't make sense, don't worry about it. We'll look at this in detail in one of the demos. But right now, I'll just focus on the architecture that when you deploy open service mesh and you have an Envoy sidecar running, the two would talk to each other in order to the yeah. So what happens is that uh, it, in its final state, you would have an OSM controller component and an Envoy sidecar sitting alongside your application. Now, as I said, that Envoy is not something that was built for Kubernetes, so it doesn't understand uh, things in Kubernetes land, things like pods, endpoint services. They're not natively understood by Envoy. So something needs to translate all of these things in the Kubernetes land into a format that Envoy understands. So Envoy APIs are called as XDS APIs, so where X can be replaced with uh, another letter, such as RELC, which is what you see in this architecture over here. Uh, and TS stands for Discovery Service. R stands for Route Discovery Service, E for Endpoint Discovery Service, things like that. So I'll talk about these components in detail on the next slide, but essentially think of them as the APIs that Envoy understands, as in these are, if you're writing a REST API, these are like the data, like the API contracts that you have. So OSM controller, what it does is it would take a look into the cluster, see how many services, what all services are there in the cluster, what all endpoints are present in the cluster, and translate them into a format that Envoy understands. And it will publish all of that data that Envoy later subscribes to. So the communication between OSM controller and Envoy happens over gRPC and follows the pub/sub mechanism. So OSM controller would publish all of this data, and Envoy subscribes to it and configures itself. That's how things work. It's not just true for open service mesh, but also for STO. Uh, so yeah, so in the last diagram, I spoke about the XDS APIs, right? The things that Envoy understands, because it doesn't really natively understand things in the Kubernetes land, right? So I want to walk you through all of those different APIs uh, within within Envoy, and they're essentially configurations that you need to send to Envoy so that it can configure itself. So let's take a look at what all of these different configurations are, and what role do they play in the behavior of Envoy. Uh, so as we discussed that Envoy can be configured both as an L4 proxy and L7 proxy. In both of those cases, the first thing you would need to configure is a listener. So listener is a way for Envoy to receive traffic. So listener is just an IP address and a port on which Envoy would be listening to traffic. Right? Once Envoy uh, gets a request, what it would do is that uh, it would send the request over to filters. So filters are uh, built like extensions in the Envoy land, just like NuGet packages or other packages which you might have used. Uh, there are also packages in the Envoy land, and they're called filters. So what these filters would do is they would try to make sense of, as in try to understand what the request is like. So in case of L4, the only meaningful information you can take out of L4 traffic is things like protocol, IP address and port. So this filter, the TCP filter, would try to extract that information out of the request and make some decisions on it. So for example, if you're sending request over to MySQL server, then the filter would be able to understand that, all right, this is the IP address and this is the port, and this traffic is meant to go to MySQL server, and it will just forward the request over. In case of Envoy working as an L7 proxy, the filters can be much more intelligent. They can unpack the traffic and also extract things like headers, cookies, routes, and a bunch of other things, path of the request. And uh, based on all of that data, when Envoy is working as an L7 proxy, another thing is introduced in the path that is called as routes. So what routes would do is, based on the data that the HTTP filter extracts, it would try to route the traffic to different services. So, for example, if the request is coming on, let's say, port 80, then it needs to go to a certain service. Or if it's going to some other port, then it can be routed to some other service. Or if a certain query string is present in the path, then it needs to go to a certain service. And if something else is present, send it over to some other service. So stuff like that, decisions like those are made at the route level. Uh, So irrespective of whether Envoy is configured as an L4 or L7 proxy, the once the decision is made on uh, that this traffic needs, as in this request needs to be processed by Envoy, it would be sent to something called as clusters. So clusters are just destination of the request. So a cluster is acts as a load balancer for different endpoints. So endpoints are IP addresses. So let's say you have a bunch of services uh, that essentially do the same thing, right? So say you have deployed your application in uh, in two versions. version 1 and version 2, and both of these versions of applications expose two and say two endpoints. So endpoint 1 and 2 would ultimately reach V1 of the service, and 3 and 4 would go to V2 of the service. Cluster would act as a load balancer between these endpoints. So if your traffic is destined for V1 of the service, it would pick one of the IP addresses of V1 of the service and route the traffic over there. So that's what the clusters and endpoints do. I will show you these configurations later in one of the demos. So the hard part is now over. So let's talk about how you can install Open Service Mesh. So as you can imagine, Open Service Mesh was built by Microsoft. So it's available as a first-class citizen within Azure Kubernetes Service. So uh, within AZ-CLI, using AZ-CLI, this OSM is available as an add-on that you can just enable. So you can see on the left that there is a command. So if you're spinning up a brand new cluster, you can just provide Open Service Mesh as a parameter to this enable add-ons uh, parameter value to the enable add-ons parameter, and it would install Open Service Mesh on the cluster for you. Or if your cluster already exists, then you can install Open Service Mesh using the Open Service Mesh CLI or using Open Service Mesh Helm chart on your cluster. So on the right, I'll just play this clip. You can see if your cluster already exists, then how easy it is to enable Open Service Mesh on your cluster, and then enable Open Service Mesh on and bring one of the namespaces within the uh, uh, OSM. So any pods that get created within that namespace would automatically have a sidecar injected to it. So there's a UI experience as well. Not something that you would use in production applications, but something good to know. Or if you're experimenting with Open Service Mesh, then you can easily get started by using the UI. So once you install OSM, let's look at some of the things that get installed on your cluster. So if you run the kubectl get command, uh, what the command that you see highlighted here on the screen, you would see that a bunch of pods get created, bunch of services that get created, services, configurations, a bunch of other stuff. But the most important out of these are essentially the uh, OSM controller service that I spoke about. So OSM controller is the control plane of Open Service Mesh. And Open Service Mesh also comes with a bunch of observability tools that you can install during the installation time. If you don't want to bring your own observability tools to Open Service Mesh, things like Grafana, uh, Prometheus, etc. You can install all of these uh, at the same time as when you install Open Service Mesh on your cluster. So once you do that, you would see that it creates services and pods for those observability tools as well. Some of the other things that get installed outside of the namespace of Open Service Mesh are some of the cluster roles. So these are the roles and permissions that Open Service Mesh uses in order to talk to Kubernetes. Remember, the OSM controller service needs to talk to the Kubernetes API server in order to find out all of the services that are running, the endpoints that are running, because it needs to translate all of that data and send it over to Envoy. So these are the roles and permissions that get installed on your cluster in order to enable this communication. Finally, a mutating webhook also gets installed. Open Service Mesh, how it works is that say you send a request to it to create a pod. Open Service Mesh is going to intercept that request and modify this request to add Envoy to the spec as well. And then that request would get sent over to the Kubernetes API server. The Kubernetes API server would read that request and spin up two pods, two containers within the same pod. One is your application pod, and another one would be the envoy pod. So that's what this mutating webhook configuration is for intercepting the request. So let's talk about the demo that we are going to use in order to understand Open Service Mesh in more detail. So the application that we are going to use, you can see the architecture of the application over on the right. So we're going to have a simple application, a book buyer application and a book thief application. Both of them would be making GET requests to another application called as bookstore application in order to buy books. This bookstore application has two versions. Both of them don't differ to each other in terms of functionality. They do the same thing. It's just that we're going to use them in order to see how we can route traffic to one of the versions of the application. So they're structured like this. The bookstore application, whenever it receives a request to buy books from the book buyer and the book thief application, it sends that request over to the book warehouse in order to replenish the stock. The book warehouse application is a stateful service. It talks to a MySQL server in order to uh, store the current stock of the books. Uh, and I used Nginx in order to expose the UI endpoints of all of these services, which we'll see. So nothing very fancy over there as well. So some of the patterns which we'll talk about through these set of applications is that how you can control which application can talk to what application. So if you want to have total control over your cluster and want to say that only these communication channels should be allowed, you can do that with Open Service Mesh without making any changes to the application code. We'll look at traffic splitting pattern. So as I said that you can send traffic to either V1, V2 of a service. Again, without making any changes to the application code, we'll see how we can do that. You can also control how the traffic is routed to services outside of the cluster or the mesh. So an internet resource, for example, you can control traffic going there as well. We'll take a look at that pattern as well, and then we'll take a look at some of the monitoring tools. So before I go ahead, I just want to talk about this, seal this knowledge that we have of communication between the control plane and the data plane by looking at these components in real life. So this is an open source application that I use. It's called KTS Lens. So essentially, if you are writing kubectl commands by hand, this is something that can make your life really easy. It gives you the view of the cluster and everything in it at a single glance. But what my intention of showing you this tool is that let's look at the book buyer application that I spoke about. If you look at the containers that are running in this book buyer application, you would see that there is this application container that's running, and then there is this envoy container which is running in the same pod. Envoy container is the data plane component. Now, in the architecture of Open Service Mesh, we saw that Open Service Mesh and the Envoy sidecar need to talk to each other in order to push the configurations, or if Envoy wants to request for certain kind of data from OSM controller, then it needs to know where the OSM controller is. So how does Envoy know where to find the the control plane of Open Service Mesh, that is the OSM controller service? So if you look at the Envoy container, you will see that there is a volume that's mounted to it during the time of creation. If you go to the volume, you can see the contents of the volume. If you expand the spec, you would find that during creation, a new cluster, a cluster gets added to the spec along with the address of the control plane components. So that's how Envoy knows that this is the port and address that I need to use in order to talk to my control plane. Right, and then there are some certificates. Don't need to worry about right now. All right, so I will show you one of the application specs. I won't talk about all of the application specs that there are because yeah, all of them are pretty much the same. So let's look at the spec for the book buyer application. Here you can see that the book buyer application is created as the spec is defined as a deployment. Nothing fancy here. It just it's a regular spec that you would use to deploy eventually any other application in Kubernetes world. Then there is a service map to it and a service account. This service account is just used to uh, identify the pod. So all of the pods running within the deployment, in this case, the book buyer pod, would get this identity, which is the book buyer identity. All other applications, the book warehouse, all of them have similar specs, which you can inspect later. And as I said that let's look at the script that I used in order to provision everything. So as I said that you can use the OSM CLI in order to set up open service mesh on your cluster. This is what this command looks like, the install command that would set up open service mesh on your cluster. You'll see that I set a bunch of flags because I wanted to install the observability tools along with it, which we'll see later. And then I created some namespaces for the applications, and I use the OSM CLI in order to add all of those namespaces to open service mesh. Remember in the AKS screenshot that we saw, you could put a check mark on the namespace, and then any pod that gets created within that namespace would get an invoice set. You can use OSM CLI to pretty much do the same thing. Then I enabled metrics on it because that's what would come up on those observability tools. I installed an Nginx, and then I did a port forward on all of the observability tools that there are, Grafana, Prometheus, and Yaga. So that's it, nothing too fancy here. But this is the live UI of all of the applications that are running on the cluster. As you can see that there is this bookstore V1 application, book buyer application, and a book thief application. You can see that none of these applications are working because we configured open service mesh in such a way that it doesn't allow any traffic to reach others by default. That reminds me that I need to bring up the slides. Yeah. So the first pattern we'll discuss here is the traffic policy pattern, which you can use in order to explicitly enable flow of traffic between different services. So you can configure open service mesh to block all traffic by default, but if you have an existing cluster and you have applications running on it, as you can imagine, that this would be very disruptive operation. You block all communication by default. So you can use permissive traffic policy mode in order to enable all communication by default, and then behind the scenes, keep writing the policies to enable communication between different services, and then on one fine day, just turn off this permissive traffic policy mode and use your policies in order to enable communication between different services. All right, now back to the demo. None of this is working. So let's see how we can enable it. So we can write this. So this is the spec that we're going to write in order to enable communication between different services. Now I'll show you how you can enable communication between the book buyer application and the bookstore application, but the rest of the specs are written pretty much the same way in order to enable the communication. The first thing that you need to write is an HTTP route group. As you can see that it's one of the SMI specs, which I spoke about earlier. And let's understand this spec in a little more detail. What this says is that there is a book spot endpoint and a buy a book endpoint, which looks like this. And this route group essentially identifies the HTTP request that you can make. That is the book spot endpoint and this buy a book, new book endpoint. So this defines the shape of the traffic that we are going to configure. Next, what you need to write is a traffic target. So this is the spec that you can write. Here, you would specify the source of the traffic, which in this case is the book buyer application, and the destination of the traffic, which is the bookstore application. In the rules, you would say that this is the HTTP, this is the shape of HTTP traffic that I want to allow, which you defined here in this HTTP route group. The rest of the specs are pretty much the same, so I'm not going to waste your time walking through those. But I will apply this spec. All right, the spec has been applied. So if I minimize the screen, you can see that the bookstore V1 application started working, and this book buyer is able to buy books from the bookstore application. This book thief application is not yet working because we didn't explicitly allow this application to talk to the bookstore application. So let's fix this problem. What we are going to do here is that enable the book thief service account as a source of traffic as well. Since it is making similar HTTP requests as the book buyer application to the bookstore application, this would function as well, just like the book buyer application does. So let's do this again. Okay. Yeah, you can see that this application has started working as well. Right? Yeah, this covers the first pattern that we have. Let's move on to the next one. So one of the most common patterns that many people that actually attracts people to service mesh is traffic splitting. So say for example, you have different versions of your service running, and now you want to selectively target one of the versions of the application. You can use traffic splitting feature of service mesh. It's available not just in open service mesh, but in mm, almost every service mesh for that case. But you can use service mesh in order to do so. So some of the key use cases on why you would want to implement traffic splitting is if you want to implement A/B testing with your services, whether version A of your service or B of your service is more successful, you can use traffic splitting pattern in order to do that. Another reason why you might want to use it is for canary rollouts. So canary rollouts at a very high level means that you have a version of service running, and then you bring in a new version of the service, and you incrementally expand its reach until it reaches 100%, so that you know the old version of the service is no longer serving the traffic when V2 rollout is complete. So that's what canary rollout is. So let's look at this pattern in action now. So we are going to first deploy V2 of the bookstore application. The spec for this application looks pretty much the same as the V1 application, so nothing very different here. You still have the same deployment and a service account and a service through which it is exposed. So let's go ahead and deploy this service. What did I change? All right. So V2 of the service is created. And I think we should be able to get some traffic served by V2 as well. All right. So V2 of the service is exposed now. And you can see that so some of the traffic has started getting routed to bookstore V2 application as well, in addition to V1 application. So let's now try to manipulate this traffic. So what I'm going to do is first apply this policy. It's called the traffic split policy. Again, you can see that it's an SMI spec through which I can specify weightage of the traffic that needs to go to each version of the service. So I can say that 100% of the traffic should go to V2 and 0 to V1. So if I apply this policy, uh, what should ideally happen is that this should no longer increment. And you can see that the book buyer is not able to make any more requests to the V1 of the service, and all of the requests are getting served by the V2. Likewise, I won't go into detail, but you can as well route all traffic to V1 of the service, and V2 of the service will remain the way it is, just by manipulating the weights. So let's look at another pattern now, which is egress management. So this particular policy is for controlling the traffic that's going outside of the cluster. So if you don't want an application workload to be mining Bitcoin on your cluster, so you want to lock it down such that none of the traffic goes outside of your cluster that is not intended. So that you can do through open service mesh. And you can also control how traffic goes to applications that are not within service mesh. So remember that you can enable service mesh on a selected set of namespaces, which means that applications that are not part of that namespace would still be able to receive traffic from applications within the namespace, right? If you want to have total control over your applications and that are within service mesh, you can use this policy in order to do that. So let's look at this egress management in action. So what I'm going to do is that I'm going to deploy a pod that hosts curl. So pretty sure many people might have used curl already. So curl is just a command that you can use in order to make HTTP requests to anything on the internet. So what I'm going to do is have a deployment which has a single container, curl container, expose it as a give it an identity to a service account, and put it in a namespace. So with this, so what I'm going to do is that I will try to make an HTTP request using that container. So if you look at this command, what it does is it uses the kubectl exec command to acquire a shell within the curl container, and then it uses that container in order to make a request to this URL http://bin.org on port 80. So what I will do is I'll bring up the terminal, paste this command. Let's see what the output of this command is. You can see that by default, open service mesh blocked access to traffic going outside of the cluster, which means that we would need to write a policy in order to enable this traffic. Now, the thing you would notice is a little different is that this is not an SMI spec, because this is a feature that's available within open service mesh, but it's not a common feature that's available across different service meshes. And remember that SMI was built to encapsulate common features across different service mesh, which means that this is a special policy available within open service mesh. So you would often see that there are two different kinds of policies that you can implement with open service mesh. One is OSM specific policy, and another one is the SMI policy. Anyway, so we'll write this egress policy. What it does is that it says that any traffic coming from this curl service account going to HTTP pin or the domain on port 80 is allowed. That's the easiest way. Sorry. To create this policy. Go back to this command and replay it. This time you can see that this HTTP request was allowed. All right. Let's look at the next one. The set of observability tools that come packaged with open service mesh. So, there are certain tools available within the CNCF portfolio that can address the observability needs of the application. So the most common ones are Jaeger that you can use for capturing traces. So traces are essentially logs structured in a special way so that they can capture the end-to-end request flow of an application. So if there are a bunch of services that need to talk to each other in order to satisfy a request, a trace would be able to capture this whole request flow traveling between different services. And Jaeger is the tool for doing this. So Prometheus is a common tool used for matrices, capturing metrics from your application. Grafana is a visualization tool that you can use in order to view the metrics. And it essentially talks to Prometheus in order to get the data. So Grafana is just the UI. It needs data that can be projected on that UI. That data comes from Prometheus. So if you have existing installations of these products on your cluster, then you can bring them to Open Service Mesh, or as we saw discussed earlier, that you can instruct OSM to install these tools for you during the time of OSM installation. So let's look at the UI of these tools. Already have them open. Because remember, I port forwarded all of the UI of all of these tools. So let's start with Jaeger. Because we have been working with these applications, so quite a few traces might have already gotten created. So if you see, there's this bookbar application. I click on Find Trace. You can see that a lot of traces have been created. You can click on any of these and you would be able to see all of the logs, etc., collected by it. Cool thing about Jaeger is that it gives you the dependency graph of the application. So as you can see, all of the requests that were made by different applications to different application, because it was able to capture the traces. And as we discussed, that traces are special kinds of logs that can track the dependency of your application as well. This is what it looks like. Let's come to Prometheus, which is a tool used for gathering metrics from your applications. You can see that Envoy is a very verbose system. It gives you access to all of these matrices without you requiring to instrument your application in any way. One of these is this container memory RSS. You can see that there is this live graph that is getting constantly updated with all of these matrices. So on its own, Prometheus data doesn't make a lot of sense. So you need to have a visualization tool for that data, which is the Grafana. Grafana, out of the box, when you install it along with OSM, comes with two dashboards, two kinds of dashboards. One are the control plane dashboards, another one are the data plane dashboards. Control plane, OSM controller, data plane are the Envoy instances that are present in your cluster. Let's look at this Envoy details dashboard. You can see it tells you how many namespaces are getting monitored, how many proxies are there, what's the performance like, duration on when it was injected, how many API requests were made, bunch of other stuff. But yeah, this is pretty much all of the UI that there is. There are a bunch of other dashboards that you can inspect as well. The control plane metrics as well. So OSM is emitting data for itself as well, so that if there are any errors, then they would be captured, would be visible on these dashboards too. All right, let's back the slides. I don't know how much time we have left.
Yeah, pretty much at time, Rahul.
Okay, sure. All right. So I will just quickly wrap up this session. So in summary, we saw what the service mesh is and what is used in the in a microservices architecture. We saw in detail what a sidecar is. Envoy is a popular sidecar that's used in most of the service mesh implementations. We saw how Envoy APIs look like, talked about SMI API, and then looked at some of the open service mesh patterns. So I'll pause on this slide for a bit, just in case someone wants to take a screenshot. Otherwise, you can access these slides on the bit.ly link as well, bit.ly/OSM-CC. That's what you can use in order to download these slides and all of the specs that I showed you earlier. Yeah,
Right,
and that wraps everything up.
Great. Thank you very much, Rahul. I just do some questions next. So we've got one from Andrew. And yeah, if you have any other questions, anyone, feel free to pop them in. Can you see that one, Rahul, or shall I read it out? All right. So
it's a pretty lengthy question.
It is a lengthy question, so you can see it. That's good.
Service mesh is specific to services running in containers. So to answer the first question, yes, open service mesh is built for Kubernetes. As we saw in the architecture, it talks to the Kubernetes API server in order to translate data for Envoy, right? So you can't run it anywhere else. If I use something simple, sure. Yeah, so if you're running things in the past land like app services or functions, don't really need to use open service mesh for that, for those.
Fair enough. Thank you, Andrew. Do we have any other questions? All right, since we're coming a little bit to the end of the time, I might ask my questions for the prizes. And yeah, thank you very much, Rahul, for the informative presentation.
No problem. My pleasure.
So tell me if my answers are right. We'll see for this. So first question: is everyone ready? All set for a jet spreading license. So there's two planes in the OSM architecture. So what are the names of the two planes? Oh, look, that's very good. Bipin, you are the winner. So send me a meetup message with your email. I think I might have given you a license before, but you deserve another one. And the second question is easier, perhaps even. So Open Service Mesh was originally made by which company before it was donated? I don't know if you can get 2 licenses. Let's see. All right, we are coming to the end of the time, and I don't know if we have another answer. So I think you deserve them both. There you go. So definitely send me a message because you'll get 2 licenses. So send me a meetup message with your email address. I'll go with Andrew's comment that you deserve the 2. All right. Well, thank you very much for joining us today. And if you've got any topics you want to talk about, definitely let me know with the meetup message. Is probably the easiest, and I can pop you on. We can talk about what you want to cover. So thank you again, Rahul, and we'll see you all next month. Good night.
Thanks, James. Thanks, everyone.
Thank you.